We focused in our past few lectures on hydrogenic atoms. Particularly, that's atoms where we have a single electron about a nucleus, hydrogen, of course, being one of them. But most atoms are much more complicated than that, and they have many electrons. And so now we need to develop the formalism for how to discuss the orbitals and population of orbitals from multi-electron atoms, so that we can move into then talking about the transitions between orbitals and how those are connected to radiative processes. So again, some of this should be familiar from your physics courses, and we'll try to move through it fairly quickly so that we can get on to radiative processes. So first off, multi-electron atoms. The multi-electron atoms, we have to extend from our hydrogenic state that we considered before to populating different orbitals, different energy levels. So instead of having a hydrogenic atom, we have to populate many orbitals and that changes the electrostatic potential, V of R, which for a single hydrogenic atom was just given by the nucleus over the radius. We need to actually populate that for the whole system. And that's complicated because that means including the interaction of any given electron with the nucleus, as well as the interaction between electrons. And we could write out the full electrostatic potential, but rather than do that, let's just think about the limits of that and how that operates. So some of the limits that you might consider is that V of R goes to something like Z of n minus 1, Z plus n minus 1, where n is the number of electrons for R going to infinity. And what that's saying is that an electron, if it's at a very far distance from the center of the atom, sees just the nucleus, all of the other electrons. It sees the nucleus shielded by n minus 1 electrons. So it's got all of these, the nucleus, and then all of the other electrons that are close into that nucleus are removing some of that electrostatic potential, and we're left with something that's just a shielded version of it. So that's an easy one we can understand. That would be a situation where you have an electron at a very high orbital number, and we don't have any others, or we have a number of other ones in closer to the nucleus. Another limit that you can imagine is that as the radius goes to 0, so as the electron moves very, very close into the nucleus, it only the nucleus matters, plus the other electrons are very, very far away. And so they just contribute a sort of constant term. So this looks very much like our hydrogenic atom with a constant term due to the electrostatic potential of the electrons that are much further out. So those are the two limits. And to fully populate the atom, you have to remember the Pauli exclusion principle. So we would have to put electrons into different orbitals according to the Pauli exclusion principle, and then solve for the full Hamiltonian of those. So what is the Pauli exclusion principle? So remember that the Pauli exclusion principle states that all electrons are identical, which means that it is not possible to say that, for example, particle 1 is in orbital A and particle 2 is in orbital B, because we can't distinguish particles 1 and 2. And so no two electrons can occupy the exact same orbital. And that is the key aspect of the Pauli exclusion principle. So no two electrons can occupy the same orbital. So this sets up a series of rules about where electrons can go in sort of orbital space, so that they are in different places and that we can calculate the energies for the full system. And when we do this, what we want to do is to solve the wave equation by minimizing the variations which put electrons into different orbitals, where the potential includes both the electrostatic potential for the nucleus of electrons and an exchange potential, which accounts for the repulsion of electrons with the same spin. Those act as variants onto the Hamiltonian, and then we look to minimize those variations so that we can minimize the energy of the system and therefore solve for the wave function. That is something that you should have done in your quantum classes, so we won't work through it in detail. But let's think about what some of the configurations could be for electrons. So what are some of the configurations? Well, we specify the atomic configuration as a series of NL values. Of all the electron orbitals. So there are NLX values, which means that there are X electrons in an orbital defined by NL. So that means there are 2 times 2L plus 1 states possible for the given atom, which is made up of 2L plus 1 values of M, because of course, remember, M can be from minus L to plus L, and 2 possible spins. So how would you write that? Well, remember, we write L in terms of S, P, D, F, and so on. So you could have, for example, a definition of a very simple atom state. The ground state of hydrogen would be simply 1, S, 1, where N is 1. S tells us that it's the sharp level, so that means that it's L equals 0. And then we have 1 electron in that state. So these are ground state values. You could also imagine having, for example, helium, which you would define. And again, we're doing the NLX definition. So helium, the ground state value would be, you could have 1s2, which tells us that we're in the ground state, n equals 1, that L equals 0, that's what the S comes for, and that there are 2 electrons in that, and they can have opposite spins. Lithium is very simple. We have to move up to having 1 more electron. Its ground state would have 1s2, the same as the helium, but then we have another electron, and that has to go into the n equals 2 S1 state. And you could move all the way through many, many different atoms, populating away as you go. If you get up to, say, sodium, then you would define it very complicated as 1s2, 2s2, 2p6, and 3s1. And you can see, of course, that we have the same as we've got for the first level is occupied like we have for helium. The next level occupied starting to be like for lithium, but they can have 2 electrons in that, and so on as we move our way up. Remember that a p level means that L is equal to 1 instead of being equal to 0. So that's a way of defining configurations, but these are actually degenerate configurations because we haven't included in our Hamiltonian terms related to the M and M sub S. Oops, better to write that as M sub S. So instead, we have to actually bring in those extra terms. We need to conclude the M term and the MS terms in our orbitals so that we don't consider just degenerate states. And that's going to mean perturbing the Hamiltonian away from its basic level, which includes just the simple central field, to include a perturbation which will include spin-orbit coupling. And we'll talk about that in our next lecture as we move on to spin-orbit coupling.